So here we are moving into chapter 8 now on solutions, and we'll discuss a variety of different types of solutions. I'm guessing when I say the term solutions, you all probably think of some solid dissolved in some solvent, and for the most part you're right, that's the type we tend to focus on, but as you'll see, there's lots of other types of solutions present in nature and in the chemistry lab. In this first section here on solutions, we'll give some background solution properties, and as I just mentioned, we might talk about some of the more exotic types of solutions. Actually, believe it or not, the most common solution that you encounter each and every day is the air in the atmosphere. It's a nice solution. It's a good link between Chapter 7 and Chapter 8 as we think about the concepts we learned in Chapter 7 on gases, and we looked at the composition of air toward the end of that chapter, and now as we think about air as a solution and move into the other types of solutions possible. Okay, so if you think way back to the beginning of the course, we talked about pure substances and mixtures, and we talked actually at that stage about solutions, at least when we use the term homogeneous mixture. So a solution would be a homogeneous mixture of two or more substances, so pure substances that are thoroughly mixed, totally homogeneous at the atomic scale. They contain a solute, that's the dissolved species, that's uniformly dispersed in another substance called the solvent. And we see here on the right-hand side, the solute is the substance present in a lesser amount. Again, that could be mass or moles, depending on how we define things, now that we know the mole concept. The solvent is the substance present in greater amounts, and again, by either mass or moles. And so here's a classic salt in water example, sodium chloride table salt dissolving in water to give us a clear colorless solution. You can't tell by looking that it's not pure water, but certainly if you're not in the chemistry lab and you taste this at home, you could quickly tell the difference between a saltwater solution and pure water. If we think a little about the nature of the solutes in the solutions, if solutes are spread uniformly throughout the solvent. So if we look at that picture on the right, the left solution there is still forming. We've got the solid down at the bottom that's slowly dissolving into solution, and we're seeing that the water molecules are starting to surround the copper and sulfate ions. As we move to the right-hand side, there's a solution that's been allowed time enough to mix, and you can see it's uniform throughout. It's the same color blue at the top as at the bottom, whereas the solution that's still forming on the left side there is much more intense down at the bottom where the solid is, and slowly dissolving and giving a very intense blue, and then toward the top the blue is very faint because few of those solute molecules have been brought up to the top at that point. Solutes are not visible in a true solution, but they can give rise to the solution. So sometimes we have dispersions where you have small particles present, and Brownian motion is enough to keep those suspended, but that's not a true solution. In a true solution, you should not be able to see, even with the microscope, the light microscope that is, the solute particles. And as we said before, the solute particles are present in a smaller amount than the solvent. Whether that amount is mass or moles, it depends on the particular solution we're investigating. Okay, table 8.1 gives us some nice examples of solutions, and as I said, the solute and the solvent in a solution can be liquid, solid, and or gas. So we tend to think about solid solutes dissolved in liquid solvents to give liquid solutions, but that's not all that's out there. Gas solutions, we can have gas in a gas, and the example I've already used is air, and again, its solvent is nitrogen, the gas that's present in almost 80%, and then oxygen is the primary solute because it's roughly the balance, the other 20%. But again, there's about less than 1% made up due to things like carbon dioxide and argon and smaller amounts of other solutes. If we think about a gas in a liquid, we've got soda water, and you've got the carbon dioxide gas dissolved in that water. Once we can see the gas bubbles come out, then it's no longer a solution, but clearly there's more gas dissolved in there than what rushes out initially when you open up that bottle of soda. Household ammonia is another example. The ammonia gas is dissolved in that liquid water. We can have liquids and liquids, and they tend to be what we call miscible. They tend to mix in very good amounts if we're talking about something like vinegar, which is acetic acid in water, or ethanol, which is ethanol in water for alcoholic beverages. You could have a solid in the liquid. Again, seawater is a great example of that. You've got a lot of sodium chloride as well as many, many other things present in that water solution. Tincture of iodine, if you've been to the drugstore to make that purchase, that's solid iodine crystals dissolved in ethanol or isopropanol, depending on the alcohol used for the liquid solvent. And then finally, we have solid solutions where you have a solid dissolved in another solid. A couple good examples would be brass, which is zinc dissolved in copper. Also, if we want to stick with copper, we've got things like bronze, which is tin and copper. The other example our book gives here in this table is steel, which is solid carbon dissolved in solid iron. It gives a much stronger solid solution compared with the iron itself. So lots and lots of possibilities for solutions, but just like you probably were thinking when you heard the term solution, we'll tend to focus on those solid solutes in the liquid solvents, but just realize that's far from the end of solution chemistry. All right, so let's pause here for a learning check. Identify the solute in each of the following solutions. So for those 4 examples, please go ahead and identify which is the solvent and which is the solute, and pause the video here while you do make those determinations and start back up to see how you did. All right, so for number 1, the 2 grams of sugar dissolved in 100 milliliters of water, which is roughly 100 grams of water. Clearly the sugar is the solute if we think about a mass, and even if we had done the mole calculation, we'd see that sugar is still present in a smaller mole amount. 60.0 milliliters of ethyl alcohol and 30.0 milliliters of methyl alcohol. Here's another possibility is we have volumes to indicate what's present in the larger and smaller amount. So the amount can be moles, it can be mass, it can be volumes. Here the methyl alcohol is present in the smaller amount by volume anyway, and so that's the solute. 55.0 milliliters of water and 1.50 grams of NaCl. Well, again, by mass, moles, volume, however we want to do that, the NaCl would turn out to be the solute here. And finally, if we have 200 milliliters of oxygen and 800 milliliters of nitrogen, well, we could use the ideal gas law, PV equals nRT. We could solve for the number of moles of each of those if we were given some temperature and pressure conditions. But if we just look based on volume, and as we know, volume and number of moles are proportional for gases, oxygen is in the smaller amount. So hopefully those were pretty simple. If you did stumble on any of those, hopefully now that's been cleared up. And if you continue to have problems, certainly please do reach out to me for some help. All right, in this course we focus on water. In 142 there's sometimes where we'll deal with non-aqueous systems, but in the first semester here we tend to deal in general chemistry, and we tend to use water as our solvent. It's also the most common solvent in nature, so that it's not any mistake that we're using water most of the time. Water is a polar molecule, so that's what allows it to dissolve either polar or ionic substances. Again, not every polar and ionic substance will dissolve in water, but many of them will. And the water can form hydrogen bonds with itself and with certain other types of hydrogen bonding molecules like ammonia, an example we used as a gas dissolved in a liquid. The ammonia and the water can hydrogen bond with each other, and that forms a really stable solution as a result. Hydrofluoric acid's another example of a nice stable solution that can involve hydrogen bonding within the water molecules and between the water and the HF molecules. So that partial positive, partial negative polarity of the water allows it to be a very good solvent for a very wide variety of substances, and sometimes you may even hear water referred to as the universal solvent, although it doesn't dissolve everything. There's ionic substances like silver chloride or lead bromide that don't dissolve to any appreciable amount in water, and therefore you have to be careful. It doesn't dissolve everything, but it does dissolve quite a wide variety of solutes. Water is particularly important for us as humans. The average adult body is about 60% water by mass. So you may have heard that life is carbon-based, and what that means is we're based on carbon for things like our proteins and lipids and nucleic acids and the carbohydrates that we use. And all that's true and good, and things that we'll go into much more detail in the next semester if you stick around. But in terms of what really makes us up, we're water-based more than anything else. Dehydration occurs when as little as 10% of body fluids are lost. It sets in very quickly. You can go for a week, 10 days without food, depending on your stores, but you can't go much more than a day without water before that severe dehydration starts to set in. And again, you don't have to drink water itself. Other liquids tend to have a lot of water, fruit juices or other things. Foods tend to be largely water as well, although drinking at least a liter or two of water a day is not a bad idea. You can get your water in other ways. Okay, so if we're going to make a solution, we need to have those components, the solute or solutes, depending on how many things we're going to dissolve, and the solvent have to be able to interact. They should have similar polarities. So a polar substance should be dissolved by a polar substance. You may have heard like dissolves like. Similibus curantur was the Latin for it that the old alchemists used. Like is dissolved by like. And that's pretty true. It's still a rule of thumb we use today. And actually, the things driving solution formation are energetics. The energy between the solute and solvent particles must be strong enough to overcome those initial attractive forces between solvent molecules and solute particles. So the reason oil and water doesn't mix is that the energetics involved in separating those nonpolar interactions among the oil molecules would not be compensated by the new water-oil interactions. The water-oil interactions aren't very favorable, so the oil-oil, water-oil interactions are much more favorable from an energetic standpoint, and that's why the separate phases remain with oil and water. If we think about salt and water, the water-water molecule interactions are quite strong. The sodium and chloride ionic bond is quite strong, but you get a lot of energy out of making new hydrated ions. So the oxygen end of the water molecule interacting with the positive sodium ions, the hydrogen ends of the water molecule interacting with the negative chloride ion. From an energetic standpoint, it's energetically more favorable to have that solution form than to have the substances stay separate instead of mixing. So here we see a visual of that process, at least of the sodium chloride dissolving in water like I described. You've got the crystal lattice, significant energy in that crystal lattice. It would take a lot of energy to melt that sodium chloride, but in order to get it to dissolve, because you're getting all of these water-sodium, water-chloride interactions that are quite favorable from an energy standpoint, you don't have to increase temperature to get the sodium chloride to dissolve. It dissolves quite well in room temperature water because of the energy associated with hydrating the sodium and chloride ions compared with keeping them in that original crystal lattice. So now we have to be careful here, and even our textbook doesn't use very careful language with solution formation. Solution formation is not a chemical reaction. It's a physical change. We can get back the sodium chloride in this example by driving off all the water. We don't have to do any chemistry to get it back. So it is just a physical change, but we ordinarily write it like a chemical change where we have the solute on one side here, the NaCl solid on the left. We show the solvent over an arrow like we do with the water here, and then we show the hydrated ions here, Na plus aqueous plus Cl minus aqueous, like it's a chemical reaction. But be careful, it's not a chemical reaction, it's a physical process, just like we talked about way at the beginning of the semester. It's a physical change to take pure substances and mix them. Solutions are a little harder to get back than a typical heterogeneous mixture might be, but again, it's still just a dissolution process. It's still just a physical change, and you can use physical methods like boiling off the solvent to get the original solute back. All right, so let's pause here for a learning check. Let's see how much sense this is making to you. Solid lithium chloride dissolves in water because, and then if you want to look through, you may have just one of those A, B, C, Ds, or E and F give you the option to combine a couple. So please read them thoroughly. Pause the video here while you reflect and make your determination, and then start back up once you've decided what you think is the best letter answer. All right, so hopefully you arrived at choice E as the best answer because both A and D are true. The lithium ions are attracted to the oxygen end, which bears the partial positive of the water molecule, and the chloride ions are attracted to the hydrogen end, which bears the partial positive. So again, just be careful. The plus and the partial plus would be repelled. That was choice B, I think, and the minus would be repelled, which would be choice C. So A and D, both processes are important and both are energetically favorable enough that the lithium chloride dissolves in the water rather than staying separate from the water like something like silver chloride might, because there's not enough energy compensation for hydrating silver ion and chloride ion to allow for solution formation in water. Okay, so that was an example of water dissolving an ionic compound like sodium chloride. Here we have water and another polar molecule, methanol here. And methanol, because it has that OH group, can form hydrogen bonds with water. So we see on the far left methanol by itself forming hydrogen bonds with other methanol molecules. We see in the middle water by itself forming hydrogen bonds with other water molecules. And then we see on the far right that we can have a methanol water solution that can hydrogen bond methanol to methanol, water to water, and water to methanol. So that's energetically favorable. It actually allows the molecules to get closer together. We have the law of conservation of mass, right? If we take 17 grams of methanol and 10 grams of water, we should end up with 27 grams of solution, and we do. But what we don't conserve is volume. We actually, because of the distance between those methanol molecules alone, when we make the solution, if we had, say, 100 milliliters of methanol and 100 milliliters of water, we might end up with 197 milliliters of solution, because we can get rid of some of that empty space between the molecules of methanol by packing in water molecules. Again, it relies on being able to hydrogen bond and having similar interactions and energetics, but that is something that happens with things like methanol and ethanol, is you do seem to lose volume because you're able to pack more efficiently when you get a water solution of those substances. Okay, and here we are, like dissolves like. I couldn't hold off until this slide, but there you see it. Two substances form a solution when there's an attraction between the particles of the solute and the solvent, so they need to have similar polarity, similar types of interactions. A polar solvent, such as water, dissolves polar solutes, such as sugar, table sugar, sucrose, and or ionic solutes, such as table salt, sodium chloride. A nonpolar solvent, such as hexane, dissolves nonpolar solutes like oil or grease. Dry cleaning is typically some sort of nonpolar solvent which can remove grease stains, perhaps, that regular old water-based washing won't be able to dissolve. So there we have it. Like dissolves like. If you have a polar solute, you likely will need a polar solvent. If you have a nonpolar solute rather, then you'll need a nonpolar solvent in order to make a solution, because just like oil and water don't mix, polar solutes and nonpolar solvents tend not to be able to have energetically favorable interactions, so they stay separate. And here's a nice picture to remind us of that oil and water not mixing. Here, instead of oil and water, we have water and methylene chloride, or dichloromethane as it's known. And in that case, the methylene chloride or dichloromethane is actually more dense. A lot of times, if it were oil and water, oil would be less dense and form a top layer. Here's an example of a nonpolar substance that's actually more dense than water, and therefore it forms a bottom layer. If we were to toss in iodine, well, the iodine will dissolve in the methylene chloride because it's nonpolar and the iodine's nonpolar, so they have good favorable interactions. But you see up in the water layer, there's not much noticeable in the way of iodine dissolving because iodine's nonpolar and water's polar. On the other hand, if we have nickel nitrate, which is a polar, really an ionic substance that dissolves well in the polar solvent of water, we get that nice nickel color in the top layer, the water layer, but we get nothing appreciable down in the methylene chloride or dichloromethane layer because the nonpolar methylene chloride will not dissolve the ionic nickel nitrate. Okay, before we leave this first section of Chapter 8 here, why don't we have one more learning check, make sure that you're getting these basic solution ideas before we complicate matters in the next section. So this learning check asks, will each of the following solutes dissolve in water? Why or why not? So for A, B, C, D, go ahead and make a determination if it will dissolve or will not dissolve in water, and then if it will, tell me why. If it won't, tell me why. Pause the video here, make those assignments, and then start back up when you're ready to check your work. All right, hopefully you took care of this learning check in pretty short order. A, sodium sulfate, yes, it should dissolve in water because it's an ionic solute. Again, not all ionics dissolve in water, but most of them, and certainly anything that's a sodium salt will. For B, gasoline, if you've ever seen those beautiful rainbows you get by the gas station on a rainy day, that's because the gasoline is nonpolar, and as a nonpolar solute, it will not dissolve in water. Same sort of reasoning for the iodine, which we saw on the previous slide. And finally, HCl, which is a polar substance, right? If we think of those electronegativity differences, the chlorine atom is holding those electrons in the bond more of the time than the hydrogen. We have a polar solute, so we should indeed get a solution. It's muriatic acid is a concentrated solution of HCl you might be able to buy at the hardware store. So to sum up Chapter 8, Section 1, most polar and ionic solutes dissolve in water because water is a polar solvent. Hopefully you've gotten that and things are going well. If not, as always, reach out. Let's try to figure out what's not going so well and how we can fix that.